Hi guys, now today we'll learn about the partial derivatives, which is just the continuation of the previous lecture derivatives. First of all, congratulations. This is the last piece of fundamental math knowledge you will need before you can build a neural network from scratch. Now let's begin. If we have a function that lives in 3 dimensions, okay, say z which is equals to 2x plus 3y. Now, how can we find the slope of that? Trick question. You can't. But we can fake it. How? You can get the derivative of this multidimensional function with respect to one of the variable at a time, treating the other variable to be a constant. Okay. So this is what known as partial derivatives. Okay. So where we treat only one variable in a multivariable equation and we keep the other variable as a constant. Okay. Now, if a function f takes two variables, that is nothing but x and y, as we can see in the above example. Now we can represent the partial derivative of f with respect to x as this, or you can simply give the delta symbol with respect to this. Okay. Now this is pronounced as del f by del x. Okay. Now how can we calculate del f by del x for the given f of x comma y, which is nothing but 2x plus 3y. Now how do we do that? Now since we are trying to find the partial derivative of f with respect to x, we will treat x as a variable, and now here y will become our constant. So now when I take a derivative of f with respect to x, let's take the first term. Now as we saw in the derivatives lecture, the derivative of 2x will be nothing but 2 plus. Now here we are treating y as constant. So here 3 is also constant, y is also constant. So constant into constant will be constant only, correct? This is a constant term. And we know that a derivative of constant is always 0. So then we got our derivative of f with respect to x. Similarly, you can find the derivative of f with respect to y. Now here what will happen is my x will become constant here because we are finding a derivative with respect to y. So we'll keep the other term as constant. And now my y, this becomes variable, correct? Now let's do that again. So now my del f with respect to del y will be, now here x is constant, 2 is constant, correct? So this term is constant and derivative of constant is 0. Plus we know the derivative of 3y is nothing but 3. So we got the answer as 3 here. So in this way you can find the partial derivatives of a variable. Now the intuition behind partial derivative is to think about how a single variable in a multi-dimensional function affects the output of that whole function. So del f by del x asks, if I only change x and keep all the variables as constant, how does the change in this x affects my whole function f of x comma y? How this output will get affected if I only change a variable x? Now that is the most important question in machine learning. What if I could find the partial derivative of my machine learning model's cost? That too with respect to a single variable, correct? As we are doing here in the same way. So then what if I am able to find a partial derivative of my machine learning model's cost with respect to the single variable? Then I could tweak that variable accordingly to minimize my whole cost function as much as possible. Again, I'll reiterate. So this calculus is the secret sauce behind how my machine learns. Now partial derivatives, as we saw here, this partial derivatives allow us to find how any variable, say here I am taking one variable x, correct? how any variable affects the whole cost of a model and then tweak it accordingly to make the cost smaller or larger. Okay, so by tweaking this, we can make a cost function, cost value as smaller or larger as per our requirements. So now here we can see we got del f by del x as a 2. That is nothing but a positive value, right? So if del f of del x is positive, then it translates to that if my x, here if my x increases by some small value, say n, then my function f, whole function f, also increases by that small value times 2. Okay, why? Because this 2. Similarly, here we can say del f by del y. If my y increases by a smallest value, say m, then my whole function, whole cost function, say f of x and y, will increase this m times 3. Okay, this 3. Now, if my del f by del x is negative, if say instead of this positive value, I would have gotten del f by del x as minus 2, then it will happen exactly opposite. That is, say if my x increases by n, then my whole cost function would decrease by n times this minus 2. So it will decrease by n times 2. Okay. So that is how this derivatives, partial derivative functions helps us in the cost functions. Okay, now let's say the cost function of the model has some variable or say some parameter called as w. This is nothing but some variable. Then and the c I will use to denote my cost function. So then the derivative of my cost function with respect to this w. Say if this is positive, means what happens is that if my w increases, then my cost function will also increase, correct? As we saw earlier. So let's do something smart. Let's decrease the value of w now. So if my value of w decreases, then obviously my c will also decrease, correct? So I'll let you work out yourself whether we should increase or decrease w to minimize the cost. If say my delta c by delta w is negative. Just think about it, guys. This is just some brainstorming ideas. Just think about it on your own. So this is the heart of a machine learning. That is nothing but called as gradient descent. So whatever we have seen till now is nothing but a gradient descent. Now let's say our cost function c has some 1000 variables. Namely, say w1, w2, like this we have how many? 1000. So this is nothing but making it a whopping 1000 dimensional function. So we noted c as cost function of w1, w2 till wn. Here my n is nothing but 1000. Now the gradient of c, okay, is denoted by, the gradient of c is denoted by this symbol. This is pronounced as nabla. So it's just the collection of 1000 partial derivatives since it has 1000 variables as its input. Look familiar? How it will be? Is nothing but cost function with respect to w1, cost function with respect to w2, like this cost function with respect to whopping 1000. So now does this looks familiar? Yeah, it's just a vector with 1000 values in it because my input is 1000 dimensional. Okay. So here nabla c, it's just a collection of 1000 partial derivatives. So this becomes my first entry and this goes till w1000. The gradient gives us mastery over the once beastly cost function. So we now know how tweaking each of the variable can change my whole cost function. You can think of each partial derivative as a dial, where turning it left, that is decreasing it, or turning it right, that is increasing it, adjust this cost accordingly. So with the power of machine learning, you now have 1000 dials to tweak at your will, allowing you to change this cost. But no human can manage this 1000 dials, let alone 100 billion that a typical neural network has. Instead, we make the network figure it out. If a machine learning model has delta C, it knows exactly each dial changes the cost and how much to turn each of them. So for example, say my this value is 1 and say this value is 9. Then we can see that this cost function with respect to this W2 variable has a bigger effect on overall cost function. So you increase the variable W2 by unit 1. If I increase this variable W2 by 1 unit, the cost function will increase by 9 factorial units. Okay. So thus the knob derivative of C with respect to W2 gives us the biggest bang for our buck in terms of changing the cost. If this explanation didn't stick, I would encourage you to rewatch the lecture again. Partial derivatives underlines the entire intuition behind how neural network works. Now let's see what is chain rule with partial derivatives. Now, I definitely promise that this is the last piece of math we need before we can fully understand neural network. Now, let's say I have a function as v, which is nothing but 3x plus 4y. Here I have x as 3a square and y as my 4b square. How can I get del v by del a or del v by del b if I am dealing with composed functions nested with each other? So you could try substituting in x in terms of a and y in terms of b to directly calculate del v of del a. If I substitute this x as 3a square and this y as 4b square, and then I can directly calculate del v by del a or del v by del b. But what if instead of this simple v function, this v could be something like 4x to the power 10 plus 4y to the power square. Okay. Then substituting this 3a square here and this 4b square here, you would end up with something like, say, 3 into 3a square to the power 10 plus 4 into 4b square ka power 2. So it will be something like 3 to the power 10, 3 into 3 to the power 10, a to the power 20. Something like will be more complex, which is lot more messier. So this is lot more messier than working with each equation separately. So now the chain rule simplifies the calculation with this complex algebraic expression by tackling them peacefully. Now let's build a computation graph. How it will be? Here is my main v. So this v is related to x and y directly, whereas this x is related to a and this y is related to b. This tree is the single most helpful diagram to draw out before computing any partial derivative. Now, if I want to find del v by del a, I need to travel from v to x, which will give me what? Let's write it here. I want to calculate this. So first I have to go from here to here and then from x to a. Right? You then multiply them together to create a chain rule. So this is how it looks. Similarly, if I want to find for b, that means say if I want to find del v by del b, what I will do? Simply first I have to travel from v to y, and then I have to travel from y to b. Another way that makes sense is the idea of fraction multiplication. Although you are not dealing with fractions at all, you can kind of see how a denominator of del v by del x and the numerator of del x by del a are same. That is nothing but this cancelling out each other, which becomes nothing but del v by del a. That is the chain, my personal method of choice for calculating the partial derivatives. The chain and the tree are the easiest way to calculate these essential derivatives. Now let's calculate all of these derivatives separately. Okay. How we'll do that is, first let's calculate del v by del y. Now my v is 3x plus 4y. So for this, with respect to y, it will treat my x as a constant. So the derivative of this will be 0. And the derivative of this term is nothing but 4. Similarly, then when I try for del v with respect to x, that time it will treat y as constant and my x becomes a variable. So the derivative of 3x is nothing but 3 and the derivative of 4y in this case becomes 0. Then next what we have is we calculate del y by del b. Okay, so now y is nothing but 4b square. So we know the rule of a derivatives of these types. That is nothing but, say I have x to the power n, then the derivative of this is nothing but n into x to the power n minus 1. So this is the derivative of this. Similarly, here I have what? 4 is nothing but constant, but here I have b to the power 2. So how it will be? 2 into b to the power n minus 1, that is nothing but 2 minus 1, that is 1, and this whole multiply by 4, this 4. So this becomes nothing but 8b, correct? So here I will write it as 8b. Similarly, if I try for del x by del a, what we get? A square, 3a square. So then when we do this, what we will get? Say 3 in bracket 2 a to the power 1, that is nothing but 6a. So now if I want del v with respect to del a, this del v by del x, what it is? Del v by del x is 3 dot del x by del a, what we got is 6a. So we have 18a. So here you can try it out for del v by yourself. All the values are here already. You just have to put it and calculate. It will be nothing but 8b multiplied by this 4. That is nothing but 32b. So once you get the hang of the notation, you will see that calculus isn't the big scary monster it seems at first. If you have cracked the chain rule and tree method and can do this kinds of calculation, congrats, you are already ahead. You are in a solid space now to start building your own neural network. So stay tuned for the next lecture in this series where we'll dive into a perceptron model, the OG of neurons. You don't want to miss it. Thanks for watching.